All right, hi, welcome back. So we're going to continue with the story of using eigenvalues of matrices to distinguish graphs. But I guess a particular topic of interest is how to show that these eigenvalues don't distinguish the graphs. And the tool that we need is cellular algebras and matrix algebras. So today, that's our plan, to define cellular algebra and matrix algebra, and then to define the other main tool that we need to discuss graph isomorphism. So we'll cover both parts of the title today. We're going to define this matrix algebras, and then we're going to give the Weisfehler-Lehmann algorithm, which is a heuristic for solving graph isomorphism. And there will be some interactive, I interact with the computer, display later, which hopefully will work. Let us continue. So I think cellular algebra has been mentioned and maybe also already defined, but let's just define what it is anyway. So a cellular algebra is a subalgebra. Immediately wrote subgraph. Oh my God, now I'm trying to write algebra of the n by n matrices over C, let's say, which is, and then now we have some conditions. Closed under multiplication. No, it's a subalgebra, so it's already closed under multiplication. It's closed under Shor multiplication, which is Shor multiplication or Hadamard product. It's the entry-wise multiplication of matrices, or as some people like to call it, like the freshman's matrix product, how freshmen want to. Sure. Yeah. Freshman's dream or something. And this thing also has to be closed under transpositions and conjugation, because these are complex matrices. And we require further that it contains the all-ones matrix and the identity matrix. Okay. So it's already a subalgebra of the n by n matrices. So it's closed under usual matrix multiplication and addition and scalar multiplication. And then in addition, it's closed under Shor product, and also transposition, conjugation, and contains I and J. So this might differ from other definitions, but for our purposes, this definition for cellular algebra will suffice. There are other names for this that may or may not coincide with what we have, but some related concepts: coherent configuration, coherent algebra. Okay, so but for us, this is what we're going to take. We're not going to require the matrices to be symmetric in particular, and it contains the matrix I, in the identity matrix, but it doesn't have to contain it as a generator, which we're about to see. So in particular, what are we interested in? Well, given a certain set of matrices, we want to consider the cellular closure, which is the smallest cellular algebra containing those matrices. So given matrices M1 through ML, we can consider the cellular closure. So it's still denoted with these angle brackets. Is there a confusion? So they're complex matrices, potentially. So it has to be closed under conjugating every entry of the matrix. So conjugate transpose will be a thing, but we're also allowing it separately. Okay. I think. Okay, so right. So it's the cellular closure, the smallest cellular algebra. The first example is something very familiar to us. So for example, for any graph X, we can consider the Bose-Misner algebra. Misner algebra, which is the closure of A of X, the adjacency matrix. Okay. So this is no.
Even if that's not commuted, we still call it a Bose-Misner.
If it's a distance regular graph,
okay,
it will be. Okay, so we can consider the following algebra, and then I'm going to call it M, just to be, Okay, this is. Oh no, let's call it A, just to look exactly like Bose-Misner algebra, to be extra offensive. Okay. Right, so you're right, Bill. That will indeed not happen. But the next line of my notes is if X is distance regular, then this cellular algebra is particularly nice in that it has two sets of bases. So it has one set of bases that are A0, the identity matrix, A1, which is the adjacency matrix. Oh yeah, graphs are X now because
They're extremely cool.
well, no, because Chris Gotzel uses X, but he wouldn't like that. No, the reason he uses them is because we use G, but often groups come up for which you would also like to use G, but then you had to use gamma. You don't want to mess up the notation in the field you're less familiar with, so you should just, you know, suffer for the graph and let the other thing be called G. So this is one basis where these matrices are the distance matrices of the graph. So in AI, the XY position is a 1 if X and Y are vertices which are distance I apart. So these are the distance matrices, and the other basis is this E0, the idempotent matrix, which is a scalar multiple 1 over n of the L1's matrix, E1, and so on. Are the distance matrices, idempotent projectors onto the eigenspaces. So I think that distance regular graphs have been defined many times. So perhaps it's not super necessary to look at them. Perhaps I will still need these numbers. So let me quickly draw you a picture of a distance regular graph. So in a distance regular graph, the only thing is that if I look at two vertices, let's say this is a vertex whose name is X, and this thing is a vertex whose name is Y. Something has to be true for the distance regular graph, which is that the number of neighbors is determined somehow by parameters of the distance regular graph. So let's say that there are some vertices X and Y, and they are distance I apart. Then what we want to do is consider the neighbors of Y. And the neighbors of Y, there are three possibilities because they for their distance from X. So I know that Y is distance I from X. So a neighbor of Y has only three possibilities. It can either be a little bit closer to X at distance I minus 1 from X. It can be at the same distance from X, or it can be a little bit further away from X. So perhaps they shouldn't have been so close together. But let's say this is a little bit closer. This is a little bit the same distance and a little bit further away. So let us just write I minus 1 here. This is I and I plus 1. Okay, so and the number of things here is C for closer, A for, oh my goodness, and B for, oh my goodness, guys, this is too much. That worked out. Okay, this was much better than the sitting and the through the line business. The skewing of the points on the line. Yeah. Okay, so the point is that there are these numbers associated with a distance regular graph, and somehow these are the only ones that you need. In general, a cellular algebra still needs to have something like these numbers, but not quite so nicely. So a cellular algebra will have the following. Where is this text showing? Okay, a cellular algebra has a unique basis. So now this is scripty A of 0, 1 matrices such that the following. So this basis is basically like the distance matrices when you consider the distance regular graph. So what's one thing that's true for those things? Well, if you sum all of them, what should I get? 0, 1 basis.
You should get the all ones.
I should get J, the all ones matrix. Great. Okay. So we're going to, oh no, okay, $sign, go back. Okay, so then the other thing is that if I sum, there must be a subset of them, A prime, which is a subset but not equal. Okay, I don't know how to make it not equal, contain. Ooh, okay, of the scripty set A. Be a subset of them such that when I sum over these, I get the identity. The identity itself need not be one of these elements of the scripty A basis. And the third thing is that for each A in scripty A, transpose has to be in also scripty A. it doesn't need to be a symmetric matrix, but its transpose has to be another one of these matrix, these basis elements. And now the third one you kind of get for free, that if for A1 or AI and AJ, we have, okay, so they're in the basis. The space is closed under matrix multiplication and linear combinations. So if I take their product, this AI, whatever this matrix is, it still lives in that matrix algebra. So it should be a linear combination of the other AIs. So this is equal to the sum, and then we'll, okay, sum index K, I'm going to fully index, and then it's a linear combination of the other AIs that are in A. And let's write them as Pijk, so that we look as much like an association scheme as possible, where these Pijks are constants. Ugh.
And the superscript K is like, it's not a power, it's just a.
Yeah. So yeah, so basically I wanted to not index things, but this scripty A should be A0, A1 up to AD, and then this K should go from 0 to D. Okay, so I think the maybe the most familiar thing for us, especially at this workshop where we have seen so many examples of distance regular graphs and association schemes, is that when we're in the association scheme, this Pijks, they're the number of, this is the number, if you have X and Y at distance K, this is the number of things that are distance I from X and J from Y. So this is the combinatorial parameter. And if X is a distance regular graph, what you can compute is like P1I, I minus 1. This is B, I minus 1, right? And so on. And similarly for the AIs and CIs. And you can get all the, and so on. And you can obtain, we can compute all other Pijk from the AIs, BIs, and CIs. So this is somehow like a very familiar setting, but slightly unfamiliar in that now I'm taking a more general concept of the cellular algebra and sort of trying to imitate the theory of distance regular graphs, but in these less nice algebras. In a distance regular graph setting, each matrix will be symmetric. So not only is it transposed another basis element, but it is the same basis element. And right, so these things, this is also just one matrix, but some other things are still preserved. So the other thing that is preserved is cospectrality. So you probably know, we have seen, so you're probably familiar with the thing that if you have two distance regular graphs and they have the same AIs, BIs, and CIs, then they will be cospectral. That if X and Y, we know that if X and Y are distance regular graphs with the same AIs, BIs, and CIs, then they are cospectral. Their adjacency matrices are cospectral. Okay, so how does this look in this more general world of cellular algebras? Well, for distance regular graphs, these AIs, BIs, CIs, they just play the role of the Pijks, all of the Pijks. So if they have the same intersection array, and you can require the same for the cellular algebra. But there's something, their adjacency matrices are cospectral, but not only that, also the Laplacian matrices are cospectral. So Laplacian matrices, signless Laplacian, and the Seidel matrices from Gary's talk.
Or by silence talking between the sum of the degree matrix and the adjacency, or in silence?
Yes, yes. So the Seidel matrices are also cospectral. In fact, if you take the same linear combination of the distance matrices in those schemes, they should also be cospectral. A1 through A0 through A. So for any A sub, the matrices, okay. So if I take M sub X to be the sum equals 0 to D of A sub I take these as the coefficients times A sub I, or the capital matrix of the matrix X. Right, I can take this matrix where this AI of X is the ith distance matrix of the graph X. And I can do the same for the other matrix, for the other graph. So this is the thing for the first graph. This is the same thing for the second graph, and I'm just going to do a little replace for each of the graphs. I can take their distance matrices, and if I take the same linear combination, whatever this has to be, these two also have to be cospectral. So this is why those three things were cospectral. All of these things, Laplacian matrices, sinus Laplacian, Seidel matrix, they are all written as linear combinations of the basis matrices of the coherent algebra of a distance regular graph. So if the algebras are cospectral or have the same parameters, every matrix has to be cospectral. Every matrix that you take like this. We believe me? Do we have to prove it? Is it necessary to prove anything in these? No.
Okay, then no.
No, okay. The proof is that each AI, you can write it as a linear combination of the EIs, and the only thing that you need is a Q matrix, the Q eigenmatrix of the distance regular graph. And then you can expand each AI in the other bases, but those are just the spectral idempotent. So the coefficients you get in this other expansion, those are the eigenvalues. But if you do the same for the other graph, you get the same numbers because they have the same Q matrix. So yeah, so maybe a quick note. These are cospectral proof sketch. We can expand both expressions, cellular algebras. And since the Q matrices are the same, the eigenmatrices of the graphs are the same, the eigenvalues will be the same coefficients we get for the other bases. Okay, so this is sort of the cospectrality that we want. So now instead of checking that two specific matrices are cospectral, what you can do is instead check that the parameters, the parameters of the appropriate matrix algebras are equal. So that's sort of what we want to do with our more complicated matrices. So what we really want is to generalize this and right. So there's one caveat. For distance regular graphs, if one of those graphs are cospectral, then the whole scheme will be cospectral. But this will not be true. So you could have two coherent algebras, and there's no single matrix in them that you can test to see if the algebras will be cospectral. So those PIJKs could be hard to obtain, which will be the case in one of the things that we're looking at. So, but this does also generalize. So this does generalizes to coherent algebras. Cellular algebras.
What do you mean them to be cospectral?
It means the PIJKs are the same. No, okay, so we're going to come to it very shortly on the next page. So this generalizes to cellular algebras, but we need to sort of formalize this process. And what is it that we need to formalize? So how did we check that these two cellular algebras in this case were cospectral? We just verified that the AIs, BIs, and CIs are equal, right? So, but in the general cellular algebras, the AIs don't come with an ordering, so you don't know which things are P, which things should map to which. So we do need to formalize this process. So we need to formalize the generalized version of the AIs, BIs, and CIs being equal. So so how to matrix algebras are cospectral, as Bill has said.
Just asking, you use the word, so I don't know.
Yeah. So they will be cospectral, and the term will be weakly isomorphic. So this will be not going to use the word cospectral. The matrices will be cospectral, but the matrix algebras will be weakly isomorphic. Okay, so this will be weakly isomorphic. But this is a mini course, so I can give you a little exercise, right? Gabriel just turned and looked at me with an expression of hatred.
Whenever you will try to answer this.
Okay, so exercise. Okay, the Wells graph, right? Also known as the Armanios-Wells graph, is a distance regular graph on 32 vertices. with parameters, intersection array, 5, 4, 1, 1, 1, 1, 4, 5. Transitive graph. It's a very nice graph. Okay, it is a distance regular graph. Those are its intersection array. So this is B0, B1, B2, B3, C1, C2, C3, C4. Is that too many? Okay, no, that's fine. You can compute the AIs from the BIs and the CI, so we don't usually write those. But this thing has the special property that it has at least 2 cospectral mates. Okay, so there are 2 graphs, which are regular graphs, but not distance regular, at least 2, who are cospectral to the Armanios-Wells graph. So part 1 of the exercise is, can you construct them? Now Bill will spend the remainder of my lecture drawing 32 vertex graphs. But yeah, I mean, it was better than, you know, trying to find GQ 416 yesterday, but okay. But the more salient point for us is that these things are cospectral, but their cellular algebras are not going to be whatever this weakly isomorphic thing is going to be. So those 2 other graphs, they are not distance regular. So if we take the cellular closure of the adjacency matrix, it's going to have bigger dimension potentially, or it might have the correct dimension, but it's not going to have the same numbers. It's not going to have the same PIJKs as this one. So maybe there is some matrix that lives in that thing, some linear combination, which certifies that these algebras are not the same. So, but also the 2 cospectral mates, maybe all cospectral mates, any cospectral mate will not be, okay, any cospectral mate will not be distance regular, So what is a good way, what is an easy way to show that their matrix algebras are not, are different? So can you find a way to show that the cellular closures of their adjacency matrices are not, I want to write weakly isomorphic, but we haven't defined it yet. So here's an exercise for when you are bored. Okay, but now let's do this and explain what is weak and strong isomorphism. So what I want to do is formalize this concept that the 2 matrix algebras, I have the cellular algebras, I compute the PIJKs, and they're the same for the 2 algebras. But the thing is I can take the same algebra and I can reorder the bases for it in some other ordering. It doesn't even have the identity, so I don't even know who should be the first matrix. And then it will be maybe even the same algebra. I mean, it will be exactly the same algebra, but the PIJKs, they will change depending on the ordering. So we do have to account for it. So let's let W and W prime be 2 cellular algebras, bases A, script A, and script A prime, respectively. Okay, so then we say that W and W prime are strongly isomorphic if there exists an ordering of A prime, script A prime, and a permutation matrix P such that, okay, so what have we achieved? There's an ordering of the second thing such that when I reorder it with this ordering, I can just send AI to AI prime with this matrix P. Prime, no, that's not the prime button. This button with the matrix P as a permutation.
You require this is 0, 1 matrices?
Yeah, there are 0, 1 bases. So in this definition, or in the thing that shortly followed the definition of cellular algebra, I claimed that it had a 0, 1 basis that satisfied some conditions.
Okay.
No one objected at the time.
No, you just,
Yes. Okay. So let's make them 0, 1 bases.
okay.
It does matter because now we're defining it. Yeah. Yeah, because this is exactly a permutation. So what you want to think is that suppose you have 2 distance regular graphs and they are isomorphic. This P will just be the isomorphism that takes one to the other. And if you order the bases the same, then this reordering is just the identity.
Well, again, my question is, you have two, this is not necessarily on one basis, like this strong in this function P, doesn't give you guys focus on the
Yeah, it does. It does. It does. So, and this is just to, no. We say that W and W prime are weakly isomorphic. So this is the thing that we want. This is our analog of cospectrality. So we're still going to need this ordering of the A prime. If there exists an ordering of A prime such that there exists a map phi takes which it's a bijection between A and A prime. So it takes A, right arrow, A prime, that after the ordering phi of AI is AI prime, and this is an isomorphism. So it preserves addition, multiplication, Shor multiplication, complex conjugation, and transposition. So it preserves all of the the properties of our all of the operations that we had to allow in our cellular algebra. It seems a little bit weird, but basically it's just any map. It doesn't even require it to be a linear map. So I don't even require that there exists some orthogonal matrix Q such that AI goes to Q transpose AI Q. I'm just asking for some map, and it preserves these things. So you will see that it will be linear. It will have some nice properties, but this is the definition that we're going to work. So, and the reason that you define it this way is that if that with this definition, and we will also not show this, what will happen is that W and W prime will be weakly isomorphic. If and only if there is a reordering of A prime such that they have the same PIJKs. And then there is a lemma. If they're weakly isomorphic, that any linear combination will be cospectral as before. So then the lemma that we desired is that if W prime are weakly isomorphic, cellular algebras, then the matrices that we had from before, so the thing that looks like this, except now we have this linear combination of AI, and then if I take the same linear combination of the AI prime, assuming that I've ordered it such that that map goes as required, they are cospectral for any choice of the sequence AI. Okay, so there's a little bit of formalization because in the cellular algebra, the eigenvalues don't work as well as before, but this will still be true. If they're strongly isomorphic, then and A1 is the adjacency matrix of some graph, then it will be isomorphic to the other graph. But this weak isomorphism is sort of the thing that we want. So the picture that we want to generate in our minds is that many of the algorithms that I've mentioned, what they want to do is they want to associate with each graph like a big matrix, and then just take the eigenvalues and distinguish the graphs based on whether or not those eigenvalues are equal. Right. So what we want to do is to take the cellular algebras corresponding to those matrices, and then they will be like some such that they will be linear combinations of the same form for the two different graphs, and then show that the algebras are weakly isomorphic, and therefore the matrices in them, no matrix in them, could possibly distinguish these graphs.
I mean, for many fibers, basis elements all have all eigenvalues equal to 0, right? It's strictly upper triangle or strictly lower triangle, the basis relations. It's talking very little about.
Yeah, exactly. Yeah.
But I guess we kind of do this for arbitrary linear combinations, right?
Yeah. I mean, if you're not very careful with the definitions, somewhat trivial things can happen. You can say, I like what I just said, that you associate the matrix with each graph. Well, you can just associate, like the 0 matrix with every graph you're given, and these things will be always cospectral. This will always fail. So, yeah. So then you wouldn't need this mechanism to deal with this scenario. But in general, yeah, and also, yeah. That's the end. Okay, so now we have this is the basic tool that we're gonna deal with. It was very simple. We just defined cellular algebra, and now we have this magic lemma that I'm refusing to prove, but works out. There is a copy in Jamie Smith's PhD thesis. So now we want to get on with life and talk about how this can be used. So the main source of matrix algebras is this Weisfeiler-Lehmann algorithm for distinguishing graphs. So the Weisfeiler-Lehmann algorithm comes in different dimensions, and the one-dimensional one is the easiest to explain. And the best way to explain it is to look at an example. So what is this algorithm going to do? This is an algorithm, or it's more of a heuristic algorithm, which computes a partition, an equitable partition of a graph, an input graph. Okay, and what you can do, you can use it to solve graph isomorphism by feeding it two different graphs and then getting the two partitions at the end and seeing if they're the same partition. And there will be some extra information because you know what the labels will be. So let me just show you this algorithm. Okay, so this is some code. That's very nice code that's been written by Holger Dell, and he's generated for us a random graph. So how does it work? In the first step of the color refinement, which is a one-dimensional Weisfeiler-Lehmann algorithm, you have your graph, and we will color the vertices based on its number of neighbors. Now there are 5 different colors because there are only 5 different degrees. There are some isolated vertices which have been colored blue. The single vertex that has 4 neighbors has been colored purple, and so on. At the next step, and at every iterative step, you now color each vertex with a list of colors of its neighbors. We iterate. I don't know what's the best way to look at this. So apparently this vertex here, this only orange vertex, is the only vertex that is adjacent to 2 degree 3 vertices in the whole graph. It's the only vertex that has 2 neighbors. Both neighbors have degree 3. That's what this little diagram represents now. And this thing is also the only one. It has 3 neighbors. One of which has degree 4, one has degree 2, and one has degree, one has degree 5, one has degree 3, and one has degree 2. There must be some class that had a more than one. Okay. So there are all these things that have yet not been separated. Okay. And then we just continue at the next step. So now this thing, its neighbors are this light blue color and also this large pink color, and we just do it again. Now we get some more okay, all right, so again we can go again, and there are somehow more colors. Right, so, and this also continues, but it's going to stop eventually because at every step we're reaching some partition of the vertices into different color classes, and we're refining the color classes at every step. So I mean, eventually you will reach the singleton partition and this procedure has to stop, right? But actually, as soon as you reach an equitable partition, this procedure will also stop. So it does have a finite runtime, and in fact, polynomial runtime. And then it will give you some coloring of the graph. And you can imagine if you have 2 different graphs, you do this procedure, you get this list of colors, but the colors have meanings. It has some multi-sets of sequences of degrees. And then if the 2 sequences are equal, the heuristic algorithm will output that the graphs are isomorphic. If they're not the same, then for sure the graphs are not isomorphic. It means that some neighborhood of some graph looks different. Okay. Happy algorithm here.
This is like the depth is like in a sense the measure of regularity. Like if you have like a finite graph and like you can't go any further, right? So,
That's right. It's immediately an equitable partition. Yeah.
There's probably the graphs, trivial automorphism.
No, but any regular graph, the color refinement will only go one step.
Look at the neighbors.
Yeah, because at the first step, they all just have the same thing. So then it's the partition, the trivial partition of the vertices, which is equitable for a regular graph. So then it stops. which is why it was necessary to do higher dimensional. Okay, so the first dimensional, the one-dimensional Weis-Fehler-Lehmann algorithm is also called color refinement. Very popular. It's used as a like a first step in many graph isomorphism routines, including that of Babai. Or yeah, the quasi-polynomial time algorithm of Babai uses this as a step. But as we have noticed, it will immediately stop after one step for any regular graph. So this is why we need a higher dimensional thing. The k-dimensional Weis-Fehler-Lehmann is as follows. By the way, this original paper of Weis-Fehler and Lehmann, it's in Russian. It's very difficult to obtain, and also, yeah, it's not really clear what was in it, given that most of the technical descriptions came from Weis-Fehler afterwards. Right. So the k-dimensional thing. Well, in our one-dimensional thing, what we did was we colored each vertex in some way. And then at every subsequent step, we colored every vertex with the colors, like the multi-set of colors of its neighbors. So this will also happen in the k-dimensional thing. In the k-dimensional, or maybe in the k-dimensional, because we're going to give the more correct version shortly, method, we color the k-tuples of vertices, the k-tuples of the vertex set. And I really do mean k-tuples. They're like ordered, not subset. So in the first step, we color it with respect to the isomorphism type, which we'll have to define more strictly in the following text. So first, in the first step, in color refinement, we just colored with degree. But for the k-dimensional thing, we're going to color with the isomorphism class, them with their isomorphism class. And then in each subsequent step, we color with the multi-set of colors of its neighbors. And the neighbors are just going to be those k-tuples that differ in exactly one position. In subsequent, we color each k-tuple with the colors, the multi-set of colors of its neighbor, which are going to be those k-tuples differ in exactly one position. So, and then we continue this way until an equitable partition. And clearly, you know, if you do a refinement at every step, you will hit some equitable partition, given that the singleton partition is always equitable. Partition into singletons is always equitable. Okay, but now you see we need to formalize some things, because now there are many things that are a little bit dubious. So
To clarify,
yeah.
if I'm understanding.
Yeah.
So let's say it's a two-dimensional Weis-Fehler-Lehmann algorithm. We've
Yeah.
got like invertices from 1 to n.
Yeah.
Then we would consider a order tuples
Yeah.
1, 2, and then
Yeah.
neighbors are going to be 1, 3 up to 1 n, and
Mhm.
also 3 to.
yeah, like x2
Yeah.
for all x. Yes, it will have a lot of neighbors. Yes, so that is one of the things you have to like be very careful about. And maybe now's a good time to sort of stop for today. But basically, the next day we will start with this Weis-Fehler-Lehmann thing, and we'll give the actual algorithm with the details. So the things that have to be clarified here are first this isomorphism class, and I think this is why they take tuples, because what you will need is for those subgraphs, if you want to color them with the same isomorphism class, those subgraphs will have to be isomorphic, and the ordering of the vertices has to be preserved. So it's a little bit stronger than just graph isomorphism of the induced subgraph. So that's the first dubious thing we had to clarify. And the second dubious thing will be exactly this thing of who are the neighbors. And they're exactly what you said. Everything will have very, very many neighbors. And then, of course, when you label with this multi-set, there's some sorting that may or may not occur. Okay, and yeah, so but what will happen next is we'll discuss this Weis-Fehler-Lehmann algorithm. In the original paper, they did also associate it with some matrix algebra. So for the k-dimensional thing, there will be some k-dimensional cellular algebra, or rather k-dimensional extension of the original cellular algebra of the adjacency matrix, such that if the k-dimensional extensions are weakly isomorphic as cellular algebras, then the Weisfeiler-Lehmann algorithm of the k dimension will not distinguish those two graphs. So that's a thing that they proved in the original paper, and we will reprove it in, well, maybe not reprove it, but we'll give some idea of how that goes and how one might achieve such graphs. Okay, so I'm out of time, right? Okay.
Is this polynomial time as k grows?
I believe it's polynomial in K. I mean, sorry, it's polynomial surfaces. Yeah, yeah, K has to be fixed. And if you choose K to be N, then you can definitely distinguish the graphs because the first step is color with the isomorphism class. So that will definitely work. But the time will be very long. Yes.
This one question. Let's then go.
no.
No, let's not. Let's.
So when the algorithm, looking at the street. Is it not?
Oh, K is 2. Yeah, so in the M's algorithm, it's going to be the matrix is indexed by arcs of the graph versus arcs of the graph. So that matrix is not exactly one of them, but it will be contained in one of them. And it's actually contained in the 2-dimensional thing. So it's like this. Yeah, but already this thing is very difficult to prove things about. I think you can show that Jaeger algebra, you would need a Jaeger algebra J4 to be weakly isomorphic to imply that the W2 are going to be weakly isomorphic. So somehow they're sort of intractable. There will be some relation with triply regular graphs, but somehow just being triply regular itself is not enough to force even this W2 to be weakly isomorphic.
For which graphs, are these obviously the multiplication?
Sorry?
So for which graphs, will the maximum memory and look at the relationship?
Oh, for those whose algebras are not weakly isomorphic, it will work, right? So if K is a fixed number, this is an efficient algorithm. It will terminate in polynomial time.
But it will not necessarily distinguish exactly.
Yeah,
So for which one will it distinguish?
well, we don't know. That's the whole point. But there was something that I did want to state that okay, do I have time? Okay, there are very many characterizations of which graphs will be distinguished from the k-dimensional Weisfeiler-Lehmann algorithm. There is a classical result of Lovash that if you count the number of homomorphisms from an arbitrary graph F into your graph G, and then count the number of homomorphisms of F into a graph H, then G and H are isomorphic if and only if these numbers are the same for the class of all graphs. So there's a result of Del Guo and Raton in 2018 that if this is the same, but not for all possible graphs F, but for those of tree width at most K, then the Weisfeiler-Lehmann algorithm of dimension K will not distinguish the graphs. So there are many characterizations. There are also peddling characterizations of some game you cannot win. You can also consider graph isomorphism as a problem wherein you have your adjacency matrices of the two graphs and you want to solve for some permutation matrix that takes one to the other, right? You can solve this as some LP or some quadratic program. And I think that you can take something called the Shirley-Adams extension, the kth extension. So yeah, the kth level, kth dimensional thing, it distinguishing the graphs will correspond with these Shirley-Adams extensions of degree K. So there are many characterizations of what it means, but it will always require you to compute some other thing about the graph. I mean, checking that the number of homomorphisms from all graphs of some bounded tree width, that's computationally hard. Yeah, right.
Okay, if we don't have more questions, then let's thank Krystal again. And then see you all tomorrow.